This word is like the raw school system, the ecosystem, the political system. This word is so general, it means practically nothing. And I will use it in this general way in addition to my special way, which is complex dynamical system. So properly, I should define complex dynamical system, which is a mathematical object, but that would take a long time, and I think it's been supplanted by this video. This video gives a better idea of a complex dynamical system than I actually have myself. See, I come to the raw school for my continuing education. Now this word also kind of a bad one, because it's a, what do you call it, euphemism, is a polite word for non-destruction, or it's a kind of double negative. Not unsustainable, it means not unsustainable. So I'm going to just put a big D for this because I think it's the destruction of the planet is really what we're talking about here. And it's proposed that there's these connections of these two ideas in a complex dynamical system of its own. That's our hope, anyway, that our study of complex dynamical systems can actually have an implication for sustainability. In other words, a mitigating effect on the destructiveness. We have to come to understand somehow what is the background or the spectrum, the biggest spectrum of the destruction problem. And also, among all these examples of the destruction process, like the environment, the atmosphere, the fishes, and so on, to try to find a crux so that we can have a leverage in education to find a crux. So this is the role of mathematics generally in the science, is to, in a class of problems, to identify the crux and regard that as a kind of a meta-problem, exists on another level. So this is what I have in mind. First, some background on the spectrum, and then this crux. I should really like to give a year-long course in that and how it might be treated in education. I think that would be the proper thing to do. Time being limited, I'm going to take just one exemplar of this crux, the demise of the fisheries. And then I want to talk about the role of math in the context of this crux as a clue to what the role of math might be for all these other parallel problems. So math had been used and misused. And our fear in being creative in mathematics is that our work would be misused more than it's used, in which case we really ought to go to the beach. So for the background, of course, these problems and our concern with them go back to prehistory. As Kieran has said, our prehistory is full of extinctions and destructions and so on. It's been part of our nature that we must try to understand throughout prehistory and history to destroy more than we create. But there was a kind of a formalization of our concern about these problems in modern society in the 1960s that we call the environmental movement. So generally, we consider the environmental movement to begin with this one especially important book called The Silent Spring by Rachel Carson, 1961. Everyone has heard of this book. I don't know how many people have read it. But we know that it, in its time, which was a special time for many reasons. The Vietnam War, the psychedelic revolution, a lot of cultural change. Medicine was in the air at the time this book was published. The Cold War, the Cuban Missile Crisis, nuclear winter, and so on. So this book was able to leverage a whole movement which is ongoing today and in which our meeting here this week, Founders Week, is devoted. The crux, I think, was identified in the same period of time, and that's a meta problem called the tragedy of the commons. And this is what I would like to talk about for a few hours, but I won't for two reasons, only one of which is obviously I don't have the time, and the other is I don't know enough. It's not really in my field, but I would like to bring it into mathematics and through mathematics and complex dynamical systems practice into the curriculum of the Ross School. This would be somehow, if I knew more about it, I would be talking more about it today, the tragedy of the commons. So Rachel Carson is that important person in the history of the environmental movement. Do you know that she was an aquatic biologist, that she worked in the U.S. Bureau of Fishes, and that her famous book, The Silent Spring, was preceded by 3 books on the sea, called her Sea Trilogy. So her concern was with fisheries, and the fishery actually is a complex dynamical system. See, here's this word, system. These are 3 different definitions I culled from the literature of a fishery, because I thought I knew what fishery meant, but I didn't really realize it was a complex dynamical system consisting of 2 things, fish and humans, as a predator-prey system. Fish, prey, humans, predators. And what happens in such systems is they spiral down to extinction in the general. See, here we have the stock, and here we have the enterprise. So these are the fish and the fishers, or the human consumers. So every time we go in a restaurant and order fish, do you know that we're participating in the plunder of the sea? So how many fish in the sea, would you guess? Something like, in a given instant, in weight, 1 billion metric tons, something like that. And how much fish people on the planet are eating every day? About 1 billion metric tons. So you're almost fishing it to extinction every day. That's how much fish we're eating. That's the problem. So these connections we might want to study through some case histories. So the tragedy of the commons is a fancy name given to this old problem of overfishing, or originally overgrazing. So Garrett Hardin, economist, he gave this name, Tragedy of the Commons, in 1968 in an article in Science to this problem, where he had a special definition for commons and also for tragedy. But really the tragedy is that there's a problem that nobody knows how to solve. But in 2009, Elinor Ostrom was given the so-called Nobel Prize in Economics for proposing a solution. And this solution is probably something that could work, but hardly anyone is familiar with her name or her theory. Here's a quotation from Garrett Hardin article in Science in 1968. It was readable. So the tragedy of the commons develops in this way, and then he gives an example. So from the example, you have to mentally extrapolate into, abstract into a universal process. There is, the commons is like a park in the middle of the town where people graze their goats. And each person grazes the goats and buys goats, grazes them, and then sell either the milk or the goat and make money. And because of the capitalist system, each goatherd wants to make as much money as possible and therefore reinvest his profits on selling a goat and buying 2 new goats, which are way less, but after eating from the commons will weigh more and then be sold and so on. So eventually, and probably in a very few years, the commons is eaten down to bare ground. That's the idea. So here are some examples of commons. I mean, everything we look at is a commons, even though we look through individual glasses and we see it as a personal possession. The atmosphere, the hydrosphere, the terrasphere, the biosphere, the networks, the electromagnetic spectrum, the energy of the sun, petroleum, and everything belongs to us as common owners of something to be used. And the tragedies are the overgrazing, the overfishing, the overmining, the overplanting, the overpollution, et cetera, In fact, there's the big D, the destruction of the environment, and from that, poverty. All poverty comes from the tragedy of the commons, combined, of course, with the population explosion, which is the tragedy of tragedies of the biggest commons of all, the planet Earth. So Eleanor Ostrom died recently, first woman ever to win this particular prize. And this is from Wikipedia. It says, her work considered how societies have developed diverse institutional arrangements. So this is the key here, institutional arrangements. She was kind of a lawyer in the International Court of the Tragedy of the Commons, and these arrangements, she called them institutions, and her books are about institutions, how you write them, how you implement them, and how you try to police or enforce them so as to actually have a strategy for, if I can use that word again, sustainability that will work. So fisheries in general are understood like this. There are the trophic levels, which are levels in the food chain. So the biggest predator is on top and the small fry on the bottom. And these are the levels in the language that fisheries scientists use for the sea. Level 5 is the top level. 1 is the bottom. So humans and marine mammals, they eat everything that's smaller than them, including the large carnivores, which are predatory fish that eat the small carnivores. And, things like herring and smelt, which are very popular where I grew up in Vermont. That's level 2. And they, of course, eat these little plants on the bottom of the sea, zooplankton and so on. So the large predators, here's a list. These are all things that we eat and all things that are threatened with extinction because we eat so much of them. And the stocks of these, the fish on every trophic level, all declining in time, and many species endangered. And the data show that the catch sizes, that how much pounds of edible fish the fishing ships bring back from the ocean and bring to the incredibly large fish markets in Madrid and Tokyo and places like that. Madrid fish market is an indoor fish market covering more than 85 acres on the outskirts of Madrid. Spain, one of the largest fish-eating nations in the world. So the catch sizes are declining despite more effort. More effort means more boats, bigger boats. We're talking about net trawlers that are almost the size of an aircraft carrier. Thousands of aircraft carriers out there catching tens of thousands of pounds of fish in a single voyage. So as the bigger fish, which are, I mean, you catch one big fish with the same effort that you catch one or two small fish, so obviously the big fish are economically more important, they decline first. And therefore, people have to fish on the next level down and the next level down. And that's called the decline of the trophic level, or also called fishing down. We fish down the chain. We exhaust one, go to the next, exhaust that, pretty soon we get on the bottom. Actually, the bottom of the sea, which is fundamental, it is the fundament for the entire food chain. The bottom of the sea is being destroyed by the weights at the bottom of the nets that are being dragged to get the larger fish. So the whole thing is being destroyed at the same time just to catch a few tuna fish, which are extremely valuable. So here's a graph where this biomass curve is in million metric tons, and this is a rough estimate by experts, so-called, of how many fish there are in the sea and all the large predatory fish in the North Atlantic, this particular data. So from 2 million down to 0, and we see in the period of 50 years, 1950 to 2000, the decline from roughly 2 to 1. So 50 years, use up half of them. So the eating rate, they do reproduce, of course, but the eating rate exceeds the reproduction rate, and therefore we're on the way to 0. Fishing mortality on this scale over here is, I think, % per year for the North Atlantic over 50 years. The number of fish killed in the fishery process has more or less doubled. See? Just an example of some, the very extensive data is available. So graphically, by species, we see here from 1950 to 2000, the catch, how many edible fish brought back. There's a lot of other ones are killed, but they're not considered edible, so they're thrown over, and they are eaten by other predators to make them bigger for our catch next year. You see, nothing is wasted in a way. And catching was increasing up until 1980 or so, and then it starts going down. And this top curve, that's herring. So they're on level 2 or so. And then the crustaceans, that's level 1. And then other fishes, and then perches and smelts, this is level 2 again. Everything showing more or less the same shape. Now the cod, this is a special case that interests me in particular, because here's where I can actually document in great detail the misuse of mathematics as a participant of this destructive process. So here it goes up, and here it goes down again, just like the others. But you see right here, there's this precipitous decline. See that? Almost vertical drop. That's the year 1992. And that's considered, that's the demise of the North Atlantic cod stock. So this is the graph of the trophic level over the same 50-year period in the North Atlantic. So we went from 3.5, that's like salmon and cod, all the way down to basically nothing but clams and oysters. That's the Northwest Atlantic. That means where the United Kingdom holds sway in the North Sea. And this is the Northeast Atlantic. That's where the Canadian Department of Fisheries and Oceans is heading up the destruction. So this is the process of fishing down. So 1968, North Atlantic cod catch, almost 1 million tons of fish. 1974, 34 tons. That's a bit of decline. So we've got other things to catch. There's always herring and smelt, they're good. 1989, TAC. The TAC is the total allowable catch. This is where the government regulation comes in. These fishermen They're capitalists, they're greedy, but don't worry, regulation will keep them in line and protect the fisheries for the future generations. The TAC, they were going to allow, this is the Canadian DFO, Department of Fisheries and Oceans, says, okay, fishermen, you can fish 125,000 tons. That would be 60% of the total stock in 1 year. That's what they were allowed. Is that what they did? 3 years later, it was set for 50% larger. That means almost the entire cod stock would be allowed to take if they had enough boats to do it. So that was in January of 1992, 185,000 tons. And 5 months later, there were no cod left. The fishery was closed by the DFO, and that's where it stands today. Cod stock in the Great Banks off Newfoundland never recovered. It will recover someday. I mean, they're not extinct. So the question is why? How can this happen? So first of all, the Canadian DFO set these standards on the basis of model predictions. The model predictions of 1992 were wrong because they didn't know about chaos theory. They didn't know that this kind of a model, a complex dynamical system, cannot be predictive. It's not possible. It doesn't have the muscle to be predictive because of chaos theory. Chaos theory is like, what does it amount to? This is the reason that nobody studies chaos theory today, is it's an inconvenient truth. Chaos theory says all the models of physical science, they are very instructive and they're great for education and improving your understanding and stretching your ability to understand complex systems, but one thing they're not is predictive. Anybody who says a prediction, like for example, the level of the ocean will rise 200 feet in the next 20 years. Was that James Lovelock? He retracted, but that was one prediction. When it comes to arguing about the past, anybody can argue about the data, but when it comes to predicting the future, you really ought to know from chaos theory that it can't be done mathematically. I explained this to Bill Thompson one day, and he says, don't worry, I have my Druid radar. And actually, yes, reading tea leaves in the bottom of your cup is better than a mathematical model when it comes to prediction. So the second thing that happened to the codfish in the North Atlantic is the Canadian department, they split they have to choose the TAC, the limited catch. They put it halfway between the model prediction, which was rather too large, and the fisher's own estimate of the population, which was way too large. They put it halfway in there. So that was a fatal dose right there. But then the fisheries minister further upped the TAC. Why? Because of pressure from the fisheries, or he was running for a re-election or whatever. So this is how it is an example of the tragedy of the commons. Anybody knows that you can't fish as you please without destroying the fishery, and nevertheless, regulation doesn't work. That's the demise. So here's my little diagram. The fishers push, the minister pushes, the DFO pushes the scientists to come up with a version of truth appropriate for the situation. This is a quotation from a wonderful book by Orrin Pilkey. Orrin Pilkey himself, a scientist involved in predicting. His field is to predict if the ocean rises a certain amount, say 10 feet, how much real estate will be lost. Well, you can't just do it naively by looking at a topographic map and looking at the level that's 10 feet higher, because the lapping waves actually erode the beach. So there's an amplification factor, and he was involved in predicting that, and through a lifetime of professional experience knew that predictions were no good. So he ended up writing this book called Irrational Arithmetic, in which many cases of such misuse of mathematics were described in detail. So the use of mathematical models is to educate, not to predict. The misuse of mathematical models is to pretend that they're predictive and beat people over the head who have math anxiety with this mystification and deception from supposed mathematical model predictions. So the math, I want to just talk briefly about the complex dynamical systems and the implications of chaos theory here. So the Fisheries predictions begin with a model of Beverton and Holt, two fisheries experts in the UK, in 1954. And their mathematical model, which was published as a book in 1954, is still in print today and extensively used. This mathematical model is truly brilliant, and it really makes good sense. And see, they preceded the chaos revolution by 20 years, so they can be forgiven for not knowing that their model couldn't be predictive. But here's the idea: you have so many cod in the ocean, say 1 million tons, and you want to graph this out by age groups. So there are different cohorts. So you get a graph here by the age of the fish, and then how many there are in each cohort. And there's a certain band of this chart, which is sexually mature or reproductive fishes that you're allowed to fish. You see, that starts at a certain age and ends a little bit before death. And these reproducing fishes, they drop eggs, and the eggs become, I don't know, larvae and small fry and juvenile fish, and eventually grow up to be sexually mature. They are called recruits. So they enter into the active zone where you can fish. And then while there, they produce eggs. So there's the recruitment, how many fishes are coming into this fishable group, and then how many eggs they're dropping. These are the two numbers that Beverton and Holt tried to relate in a mathematical model. And another example of the misuse of mathematical models is a few years later, which is the origin of, complex dynamical systems. We're not supposed to speak such words in the raw school without giving their entire history. So complex dynamical system begins in the 1950s in the work of J.W. Forrester, who was trying to analyze business cycles in General Motors or other large industries. Complex dynamical systems, also known as system dynamics, at that time in the 1950s was called industrial dynamics, but pretty soon he was recruited to treat a bigger problem, the population explosion. And the Club of Rome, group of industrialists in Europe, identified what they called the world problematique. And that is that, yeah, we know the population bomb, exponential growth of human population, is going to destroy the environment. We know that, and no matter what we try, we can't do anything about it, and that is the world problematique. It's not the population explosion itself, it's our inability to do anything about it. And what is it? It's yet another example of the tragedy of the commons. So none of these problems, including that one, we can solve. But J.W. Forrester thought that with a complex dynamical system, he could actually model and predict and use the predictions to beat human population over the head and get them to quit reproducing. And so this model, which took thousands of dollars, 1,200 experts, a couple of years, invention of a new computer language still used, and he gave his prediction in 1971 of the limits to growth. He said, the resources of planet Earth will be exhausted in 1 century. A couple of years later, they revised it. Said it'll all be over in 10 years. So they didn't intentionally deceive us. They innocently deceived us because they didn't know about chaos theory. They thought their models could be predictive. So the Beverton and Holt theory preceded the chaos revolution. But here is this is the cover of their book, or at least a recent republication. And it's a beautiful job of applied mathematics, I think spectacularly beautiful. When you go inside, I've bought a copy. On page 57, you find this really amazing drawing that you follow. This relates egg production and recruitment, those two variables I described. And here's what happens. Certain number of eggs gives certain number of recruited, gives certain number of eggs, gives certain number of recruited, and you go around and around and around, and you get the cobweb, which is by now well understood as the very icon of chaos theory. It's studied extensively since 1970 under the name the logistic family. So it's a model chaotic system, and here indeed is their data from it, which they say successive values of recruitment and egg production follow a disturbance. The lower part shows these changes, the steady states, blah, 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 the dynamics, the permanent oscillations follow even a transitory disturbance. So these people, if they had thought about what their own model predicted, would have been the original discoverers of chaos theory, which they didn't. It was 10 years later that in Japan and at MIT, chaos theory was officially inaugurated. So that is, they can be excused in their ignorance. Orrin Pilkey in his book, Useless Arithmetic, has these examples: fishing, Yucca Mountain, rising sea level, abandoned mines, planned invasions. So fishing was the first chapter in the book, and it's from there that I got most of the original information that I have told you about the demise of the codfisher. So here's just what I want to tell you, that NetLogo, which is the teaching tool that we use here to teach everybody about systems theory by extensive experience of computer simulation of complex analytical systems. It actually comes equipped with a family of models called the NetLogo Model Library, and one of them is a model for the tragedy of the commons. So here you see it. It's a HubNet model, and that means it's set up for what they call participatory simulation. That means we could do it right now, given time. Everybody in the room with a laptop could sign on to be a fisherman while we simulate the fish and the fisherman, and each one then pursues to try to make the maximum profit, or if they see that the fishing is going to end soon, and maybe make some kind of agreement. And what is not included in the model, which I think could be developed here by students in this school, is to include the institutions of Elinor Ostrom within the NetLogo model to experience, to investigate whether or not, in practical terms, in our society, the solution of the tragedy of the commons is possible with some kind of agreement and compassion, sympathy, resonance, and so on, compassion of each other as a group, and come up with a solution which then would be part of their education carried forward as a voters' future ministries of fisheries and the like. So beyond that, I propose a better kind of model in which the people who eat the fish, the government, including the Canadian Department of Fisheries and Oceans, and also the Canadian Minister of Fisheries, and also the fishery itself, which is a complex dynamical system in the style of Beverton and Holt, that this fishery has predators and prey in its own complex dynamical system. This should be modeled with a brand new NetLogo model to try to understand the dynamics of, investigate questions like, is regulation possible in a capitalist society, and things like that. How large a change in our operating system would be necessary to eliminate the bug that is killing the planet. So in some, CDS models cannot predict, but they can educate. So some written version would be available someday.